Hello everybody, and welcome back to another Big Ideas lesson. Today, section 4.4, factoring polynomials. We're at the halfway mark, y'all. Let's do it. We know how to factor quadratic expressions in a lot of different ways. So there were 5 main ways that we talked about last time. Or I should say 2 units ago. My apologies. We learned that the first thing we should do is check to see if there is a greatest common factor. We then check to see if we can factor it by grouping. Remember that grouping really only works when you have 4 terms. We can factor using our big X, which you've heard me call the combinator, but I did want to let people know that this is not the official name of it. This is just the Mr. Strager name for it because we don't really have another name for it. We learned how to factor using the AC method if you have an A value in front of your trinomial. And we've also learned how to use the difference of two squares pattern. So there's a lot of different methods we've learned. Turns out all of these methods work for polynomials too. We just have to be very careful because with polynomials, they can be a little bit tricky. A lot of times when you think you're done, you have to double check and make sure that everything is as factored as it can get. We call this being factored completely. A polynomial is factored completely when not a single one of its factors can be factored further. Usually if you have an x squared somewhere, it can still be factored, and binomials usually can't be factored, so like x minus 4 can't. But with every rule there are exceptions, so we just have to be careful and aware of our factoring methods. So for example 1, we are going to factor the following using the greatest common factor. If, after we take out the greatest common factor, it's totally done, great, we can explain why. If not, we want to factor it until it is completely factored and explain why we're done. So factoring out the GCF means taking out the greatest common factor. Let's look at this first one. Is there a greatest common factor that's in common between all 3 terms? Turns out there is. All of these terms have an x in it. So we can take out the x and write down what's left over in parentheses. Well, what's left over is x squared minus 4x minus 5. Nice. Now we need to ask ourselves, are we done? Well, we can't take out a greatest common factor. We can't factor by grouping since there's only 3 terms. Can we factor this using our big X or a combinator? I wonder if we can. Let's see. If I put negative 5 on top, meaning I'm multiplying to make negative 5, and I'm trying to add to make negative 4, are there 2 numbers that do this? Are there 2 numbers that multiply to make negative 5 and add to make negative 4? There are. Negative 5 times 1 is negative 5. Negative 5 plus 1 is negative 4. So we can factor it further. We can factor it as x, because that's just going to stick around, times one of our factors will be the first one, so x minus 5, times x plus 1, since that's the other factor. Now we ask ourselves, are we done? Is this factored completely? And how do we know? Well, let's check all these factors. X can't be factored further. X minus 5 can't be factored further. There's nothing we can take out or factor this as. Same with x plus 1. We know we're done since every term is a simple binomial, so like these ones, or x. We're done because all of our terms end up being simple binomials and our x term. There's no copy and paste answer to tell if it's factored completely. We just have to say, okay, in this answer, I can tell that none of these can be factored, and why. Let's see the next one. 3x to the 5th minus 48x cubed. I actually want you to try this one out on your own. See if there's something you can take out of it, and try to remember our patterns, hint hint, to see if it can be factored further. Pause the video, try this one out real quick. Hopefully we recognize that out of both of these terms, we can factor out 3 and x squared, or x cubed. We can take out 3 x's from both of them, and both of these can be divided by 3. So what's left over when we do that? Well, we'd be left with an x squared over here, and if we take out 3x cubed from this, we're left with minus 16. Let's run through our checks. Is there a greatest common factor? No. Can we factor by grouping? No, there's only 2 terms. Factor using the big X? No, there's only 2 terms. Factor using the AC method? Mr. Strager, there's only 2 terms. But can we factor using the difference of 2 squares? It's certainly a difference because there's a minus sign. X squared is a perfect square. And 16 is a perfect square. So yes, we can factor this using the difference of 2 squares. We write down our 3x cubed because that's what we took out at the start. And remember that the difference of squares pattern says the following. According to the difference of squares pattern, we're going to get 2 binomial factors. It's the square root of the first one plus the square root of the second, and the square root of the first one minus the square root of the second. The square root of x squared is just x. The square root of 16 is 4. And the square root of x squared is x. The square root of 16 is 4. Here is our answer. And once again, this looks like it's factored completely. How? Well, 3x cubed can't really be factored, per se. It's just a single term. And these binomials are as simple as they can get. We can't factor anything out of them either, so we're good. Last but not least is this problem. And again, I want you to try this on your own. Pause the video, try it out. We'll come back and do it together. In this third one, there is a common factor to be taken out here. We can take out 4x from everything. If we do, we'll be left with an x squared. Here, we'll be left with plus 7x. And negative 36x divided by 4x is negative 9. So we ask ourselves, can this be factored further? Is this factored completely? There's no GCF. We can't group it. But look, it's a trinomial with no a value. We can just use our big X, right? We can just use our combinator. So we try to find what multiplies to make negative 9 and adds to make 7, and we're stuck. Let's think about these factors of 9, right? You could do negative 3 times 3. That would give us 9, but then this bottom one would be 0, so that's not going to work. You could do maybe negative 9 times positive 1, but that's negative 8. Maybe positive 9 times negative 1. Oh, but that's just positive 8. Nothing works here. There's no number that works to make this combinator happen. So actually, we can say this is factored completely. This is one that if we wanted to solve it, we would have to use quadratic formula or completing the square to solve. There's no way to factor this. This is factored completely since x squared plus 7x minus 9 cannot be factored. It is unfactorable. The fancy word for this is that x squared plus 7x minus 9 is irreducible, or a prime polynomial. But we're not going to use those words. We can just say it can't be factored. If you want to be fancy, though, you could totally say that it's irreducible, and your next math teacher is going to have their mind completely blown. Down here, notice that for one of the problems, we used the difference of 2 squares. There are some other patterns that we can use to help us out. that we must keep an eye out for. These are non-optional. If you see these, you must factor them using these patterns. These ones are much trickier to memorize. Much, much trickier to memorize. But we'll get some practice with them. We'll see how we do. The sum of two cubes pattern. If you have the sum of two things that are cubed, sum means addition. Maybe we have x cubed plus 8. You don't actually need to factor this. We can just write out our answer because it's a pattern. And the pattern goes like this. Your first factor is just a plus b. In other words, it's the cube root of your first term plus the cube root of your last term. Remember that a cube root is just asking what number times itself 3 times makes x cubed, or makes 8. The cube root of x cubed is just x, because x times x times x is x cubed. But what number times itself 3 times makes 8? It's not 1 times 1 times 1, that's just 1. But 2 times 2 times 2 is 8. We've got our first factor down. Our a is x, our b is 2. Well, now the next part says that we just have to take a squared. We said our a was x, so that's x squared, minus ab. Okay, our a is x, our b is 2. That's minus 2x plus b squared. b is 2, b squared is 4. Dunzos. We are good to go. But we always want to ask, can this middle term be factored? In other words, are there two numbers that multiply to make 4 but add to make negative 2? And most of the time, your answer is going to be no. Most of the time, your answer is just going to be straight up, nope, not possible. This is as factored as it gets. Let's see if we can do a difference of two cubes as well. The sum is when they're added. The difference is when they're subtracted. So let's do something similar. Let's do x cubed minus 8. Ooh, we've got a difference now. But again, the setup is pretty much the same. This time, your first factor is a minus b. Our a value is x. Our b value is 8, so it's our x minus 8, or x minus 2, blah, times a squared plus ab plus b squared. So for this one, we can do a squared is just x squared. ab is negative 2 times, just 2 times x, so it's going to be plus 2x. Remember that when we talk about b, we're just looking for the number itself that makes that. And then b squared, b is just 2. 2 times 2 is 4. But again, we always have to ask, are there two numbers that multiply to make 4 and add to make 2? Nope, we are good to go. This is factored. We're going to have to get some practice with using these patterns. So the first bit of practice here is identifying those patterns. Seeing, okay, there's a pattern here, can I practice it? I want you to actually try out these 4 problems on your own. Afterwards, we will talk about the patterns. Try these out, pause the video, come back in a little bit. All right, here's something that might be able to help us for all of these. For the first one, 125x cubed is big. But what times what times what makes 125? And it turns out there is a number. It's 5. 5 times 5 is 25. Times 5 is 125. So our first factor here is 5x plus, what's the cube root of 8? We already talked about that in the last page. That was 2. So that's the first factor, 5x plus 2. That's the easy one. The trickier one is going to be finding another factor. Next up, we have to follow the pattern. The first term is a squared. Well, a squared means 5x squared. 5x squared means we should do 5 squared. It's 25 times x squared. Just x squared. If we look at the pattern, the next thing we have to write down is minus ab. Well, here, our a is 5x, our b is 2, so it's minus 10x. And last is b squared. B squared is 4. Once again, it's going to be one of those cases where you will not have another way to factor this. This is just good to go. In fact, all of these difference and sums of cubes will be good to go straight off when you're done with it. There's no way to factor them further. Over here, we have 1 minus x cubed. Well, that's just going to be 1 minus x as our first term. Remember that if it's a difference of cubes, it should be 1 minus x, or a minus b. 1 squared is just 1. This time it's plus ab. Well, our a is 1, our b is x, so it's just plus x. Last off, we have plus b squared. In this case, our b is x, so it's plus x squared. This doesn't look quite right, though. It's always nice to put things in standard form. So I'm going to rewrite this as almost did a doozy there. 1 minus x is not the same as x minus 1. It's negative x plus 1 times x squared plus x plus 1. Whew. Caught myself. Your answer to this one down here is going to be a little bit trickier because you may have noticed there's something you can take out of here, isn't there? We notice that these two terms have a lot in common. They can both be divided by 2. So, we take out a 2 from here, that gives us 8. We take out a 2 from here, that gives us 27. And they can also be divided by x squared. So we get 2x squared on the outside of our parentheses, and we're left with 8x cubed plus 27. These are both perfect cubes. So we know that we can use our sum of cubes pattern. We get 2x squared, because that's just going to hang out. What's the cube root of 8x cubed? What times itself 3 times makes 8 and x cubed? Well, 2 times 2 times 2 is 8. And x times x times x is x cubed. Last, what's the cube root of 27? It turns out that 3 times 3 times 3 is 27. So that's our first factor. Our next factor is going to be a squared. That's just 2x squared, which is 4x squared. Minus ab, it's minus 6x. And then we have our final term, which is b squared. That's just going to be plus 9. And we're good to go. You see how these patterns may look a little bit strange, but they're actually much easier to implement than you know? The more practice you get, the easier they get to use. Last, we have 64x cubed plus 27, and we're lucky because both of these are just straight up perfect cubes. 64 is 4 times 4 times 4. So we can write this as 4x plus, we know from the last problem, the cube root of 27 is 3. So 4x plus 3 times 4x squared. Well, 4 squared is 16. X squared is just x squared. Minus ab, that's 3 times 4x, that's 12x, plus b squared is 9. Good to go, once again. So these special factoring patterns are scary at first, but the more practice you get with them, the easier they are to use. Down here, I just want us to review factoring by grouping. Factoring by grouping works like this. This is a good first problem to do it with, and a good second problem to do it with as well. You look to group all of your terms, but before you do, ask, is there anything in common with all 3 of them, or all 4 of them? No. And you can only do grouping when there are 4 terms, so this is perfect. We're going to group together the first 2 and the last 2 terms. From here, we see what they have in common that we can take out. So 2x cubed and 9x squared can both be divided by 3x squared. So we have 3x squared. And in parentheses, we want to write what's left over. If we divide 12x cubed by 3x squared, we get 4x. Negative 9x squared divided by 3x is just negative 3. So 4x minus 3 is our term. But 4x and negative 3 don't have anything in common. There's nothing we can take out. So remember, if there's nothing that we can take out, we take out a 1, since you can always divide by 1. But that just leaves us with 4x minus 3. Now we just have to put it all together. Our terms on the outside become a factor, our terms on the insides become a factor. So we pull out the 4x minus 3. That's one of our factors. Our other factor is whatever was outside, 3x squared plus 1. Try the next one. Remember, try to see if there's something you can take out at the start, or a greatest common factor. Group it, and make sure all of your final terms are as simple as they get. Pause the video, try it out, and we'll come back in a minute. So let's get started. Is there anything that's in common with all these terms? Yes, all of them have an x in it. So let's start by taking out the x and writing what's left over. We'd be left with 2x cubed plus 5x squared plus 6x plus 15, since all I did was I lowered all the powers by 1. That's what happens when you take out an x. Now we see if the rest can be grouped. Well, we group together these 2 terms. I'm going to use square brackets because double parentheses just don't look right to me, but you can use parentheses if you like. And let's see what's left over. So I have my x still on the outside, but on the inside, what can I take out from 2x cubed and 5x squared? X squared is the only thing these 2 have in common. So it's x squared times what's left over is 2x plus 5. Good so far. What can I take out from positive 6x and positive 15? Well, both of those can be divided by 3. So we take out a 3, leaving us with 2x plus 5. We know we did it right because the middle terms match up. So when we write out our final answer, we get the following. We get x times the stuff that was in common, 2x plus 5, times the stuff that we took out, x squared plus 3. Done! And this can be factored no further. Very nice. For the bottom problems here, it says to factor using any method of your choice. Some of these are a little bit tougher. Try some of them. Try a couple, see how we do, and see if we can identify the best way to factor them. I'm going to be putting up the work in a second. I'm not going to be walking through these ones. But if you have questions on a specific one, let me know in class. Pause the video, try some of these out. How did we do? Most of these we talked about in Unit 2. We're just sort of expanding it from here. For instance, we know that this is a difference of 2 perfect squares, but even one of the perfect squares is a difference of 2 perfect squares. We've reviewed grouping, we've reviewed all of this. But this one's a little different. This one, there's no a value, so it seems like we can set up a combinator, right? Finding 2 numbers that multiply to make 20 and add to make negative 12. Heck, maybe even found those 2 numbers. Maybe you even found that it was negative 10 and negative 2. But the difference here is we have x to the fourth and x squared. It's bizarre. But you know how I said all of our rules apply to polynomials as well? Well, we could, if we wanted to, write this out like x to the fourth minus 2x squared minus 10x squared plus 20. Because negative 2x squared minus 10x squared is just negative 12x squared. And we could factor by grouping here. We can use all the tricks that we've learned up until this point. We would get x squared times x squared minus 2. And out of these two, we could take out negative 10 and be left with x squared minus 2. So the answer to this one is just x squared minus 10, x squared minus 2. Technically, we didn't even need to use the AC method here. We could have just said x squared minus 10 and x squared minus 2. We're just so used to using x, where it's x minus 10, x minus 2, that we don't usually think about what we have to multiply to make x to the fourth. But in this case, x to the fourth, x squared, all this points to us using x squareds. Last but not least, we're going to learn about the factor theorem. This is going to be the groundwork for a later lesson where we're going to learn some more precise ways of finding factors. So in section 4.3, we learned how to divide. Remember how we did synthetic division? The key was that if you divide by a binomial x minus k, you can use synthetic division. It's easier to divide. But how do we know what a polynomial is divisible by? Like, how could we know to divide by x minus 4? There is a way to check. In fact, there's a couple ways to check. So given that a factor x minus k, we know that whatever k is, that'll be a 0 for our polynomial. We know this because we learned about factored form back in Unit 2. We know that in intercept form, you get something like f of x equals x minus, or a times x minus p times x minus q, and p and q are your zeros, or your intercepts. We know about this. We're just using the letter k here. Whatever k is will be a 0, or a x-intercept for this polynomial. So if we can set f of k equal to 0, we'll know that x minus k is a factor. In other words, and here's the key here, by plugging in k for x, as long as we end up with 0, x minus k is a factor. That's a lot of variables, but let's see it in practice. Let's say we wanted to figure out if x minus 2 is a factor of this polynomial. Sure, we can factor this by grouping, but I'll tell you this much, the next one will be a little bit difficult to do by grouping. To determine this, we can plug in our k value and see. So what we're saying is, what's our k value? Our k value is just 2. Remember, it's x minus k. If we plug in a 2 everywhere we see x, what it's saying is we should get it equal 0. If it equals 0, we've got a factor. X minus 2 is a factor. If we don't get something that equals 0 when we end up evaluating this, x minus 2 is not a factor. Let's get to it. So instead of x cubed, we'll have 2 cubed. Instead of 2 times x squared, we have 2 times 2 squared. A lot of 2's. Instead of minus 5x, we have minus 5 times 2. And we have minus 6. Let's do this bit by bit. What is 2 cubed? Well, we've heard enough times so far. 2 cubed is 8. What's 2 squared times 2? That's another 8. Negative 5 times 2? That's negative 10. And we have a negative 6 at the end. What is 8 plus 8 minus 10 minus 6? 0. Since when we plug in our k value of 2, we get 0, x minus 2 is a factor. We say x minus 2 is a factor since 2 is a 0 of the polynomial. 2 is a 0 of the polynomial, so x minus 2 is a factor. This is going to come up again. Keep in mind, if you get 0, it means this is a factor. Or you could think of it backwards. If you have this, you know that it's one of your zeros. Let's see the next one. Let's see example 6. Determine if x plus 5 is a factor of the polynomial 2x cubed plus 24x squared plus 47x plus 61. We could just try dividing it out and see if we get a whole polynomial, or we can just plug in our k value. What's our k value here, though, if we have x plus 5? Our k value is minus 5. Be very careful. It's always x minus k. So we're going to plug in f of negative 5 for all of these. Try this one out on your own, and we'll come back in a second and display the answer. Pause the video and try it out. How'd we do? We end up getting that f of negative 5 equals 176. That is not 0. So negative 5 is not a 0 of this polynomial. In other words, x plus 5, not a factor. Not a factor since negative 5 is not a 0 of the polynomial. Perfect. Here's a little bit of a challenge. I'm giving you a polynomial now. X to the 4th minus 7x cubed plus 7x squared plus 15x. Could you find a binomial factor, x minus something? Feel free to guess and check different values of k until you find a factor. Then try to factor the polynomial after you find that factor. And here's my hint to you. I used single-digit positive and negative numbers for k. This is a challenge problem, so try it out, but don't feel bad if you want to watch along as well. Pause the video if you'd like to try it, though. Let's get started. The best thing that we could do is we could try to guess and check. And when we're guessing and checking, let's organize our work a little bit. I'm going to write a table. I'm going to personally start with positive numbers. And as I go through, I want to see what happens when I plug them into f of x. So I'm going to try 1, 2, 3, 4, 5, 6, and we'll see if any of those work. The first one that does, I'm going to stop. So if we plugged in 1 for all of our x's, we get 1 to the 4th minus 7 times 1 cubed plus 7 times 1 squared plus 15 times 1. 1 to the 4th is 1. Negative 7 times 1 to the 3rd is just negative 7. 1 to the 3rd isn't anything special. 1 squared is 1 plus 7. 15 times 1 is 15. We can already tell this is not going to work. So 1 is not a good k value. Maybe we try 2. 2 to the 4th minus 7 times 2 cubed plus 7 times 2 squared plus 15 times 2. Maybe this will work. 2 to the 4th power is 16. 2 to the 3rd is 8. Times negative 7 is negative 56. 2 squared is 4. Times 7 is 28. 15 times 2 is 30. Ooh, hold on a second. This is 16 minus 56 is negative 40. Plus 28 is negative 12. Oh, but plus 30 is going to give us positive 18. So that's a no-go. Let's try it with 3's. 3 to the 4th minus 7 times 3 cubed plus 7 times 3 squared plus 15 times 3. We're starting to get up there, and we're starting to find that's getting a little harder to do the math. Like 3 to the 4th is 81. 3 cubed is 27 times negative 7. That's going to be a huge number. 27 times negative 7 is negative 189. 3 squared is 9 times 7 is 63. 15 times 3 is 45. I don't know about this one, guys. Let's see. In fact, let me use the calculator for this one. So if I bust out the calculator, we're going to do 81 minus 189 plus 63 plus 45. Oh my gosh, we got it. It's 0. So what does that mean? It means we found a factor. Our factor is x minus 3. Fantastic. But it then asks us to factor the polynomial completely, and that might be a little trickier. But we know a factor, right? Here's where we have to put our thinking caps on. Factoring is just division across parentheses, right? Is it possible that we could do synthetic division to find what this divided by this factor will be? It sounds crazy, but yes. And there are faster ways to do this problem, I should say. Many of you might even know the faster way just by looking at it. But if I was to give you a 5-term polynomial, this is basically the only way to do it. 4 terms we know how to group. So let's do synthetic division. Our 3 is going to go on the outside, our k value. Then we put all of the coefficients. Well, our coefficient for the first one is just positive 1. Our coefficient for the second is negative 7. Our coefficient for the third is positive 7. Our coefficient for the fourth is 15. And don't forget, we don't have a constant term here, so we can just write that as 0. Let's do synthetic division. We carry down the 1. We then see what's 3 times 1. That's 3. According to the next step, we add these together to get negative 4. And we repeat the process. What's 3 times negative 4? It's negative 12. So we do 7 plus negative 12, giving us negative 5. What's 3 times negative 5? Well, 3 times negative 5 is negative 15. What's 15 times negative 15? 0. So we actually end up with 3 times 0 is 0. 0 plus 0 is 0. We end up with no remainder. Remember that the last number in synthetic division is no remainder. We could write it as 0 over x minus 3, but 0 divided by anything is 0. So we can just write out the rest of this polynomial. We have a plus 0 at the end. We have a minus 5x. We have a minus 4x squared, and we have a x cubed. So our factors are x minus 3 and x cubed minus 4x squared minus 5x, like that. We might see something we can factor out here. We see that we can factor out an x from all these terms, so let's rewrite it once again as x times x minus 3 times x squared minus 4x minus 5. And can this be factored? If you're paying attention to one of the problems on the first page, you know that this is actually one of the problems we already factored. We factored it as the following. We factored this as x plus 1 times x minus 5. This is totally factored now. Isn't that crazy? If I was to give you a problem that you couldn't factor by grouping because it was too long of a polynomial, this is what you would do. You would try to find a factor x minus k. And we are going to learn ways in the future of finding those even easier. For now, however, that is the end of our notes for today. As always, if you'd like some more practice problems, try the problems on the next page. We've got plenty. With that said, have a fantastic rest of your night.